So this is how you go through the process of refining one of these solvers. And so for your particular problem, this is the process you're going to want to go through till you get to a point where the solver is scalable, meaning the number of iterates is pretty insensitive to the size of the problem, and it's efficient in the sense that it's scaling well with the number of processes and with the size. And so most of pilot performance for the problems we've looked at so far is really determined by the linear solver. Now, as you start to get into more advanced formulations, namely nonlinear material properties or nonlinear constitutive relations on the fault, that's not going to be true anymore. And so you saw with Brad, well, not this session, you'll see with Brad during the fault friction tutorial that there's a lot of subtlety involved in the nonlinear system solution. So I just want to try to give you the same kind of introduction to the nonlinear systems, although I realize that it's a lot more underdeveloped. And this really reflects the state of research in this area too. Nonlinear solvers, even though they're incredibly old, they're also incredibly hard, and therefore there's not nearly as many concrete things we can say as for linear solvers. So what I want to do is I want to show you a simple problem, not pilot fault friction, because that's much more difficult, and I'll leave that for Brad. I just want to try to illustrate some things about the nonlinear solvers. So what this is a lid-driven cavity. So it's basically the Stokes problem, and this Grashof number, since I'm going to keep the Prandtl number at 1, this Grashof number will be the Rayleigh number. So you can think of this example as the Stokes problem for a high Rayleigh number, which is not all that far away from the pilot problem for a difficult frictional relation. It's different, but it has some similar characteristics. So any of you can run this exact problem in your PETSI install. And these options should be familiar, although I'm going to run on a regular grid, which allows me to do a lot of interesting things easily. So what happens? So here we have Prandtl number of 1, Grashof, so this means that the Rayleigh number is 100, and we can see we get nice, initially the Newton iterates have to come into the basin of convergence, and once you do come into the basin of convergence, you double the number of accurate digits every iterate. That's quadratic convergence. So this looks great. We can try higher Rayleigh number, and this still looks great. However, you're going to get into a regime where you get close to turbulence. Now, it's not turbulent until you get to maybe 10 to the 6 or 10 to the 7. But once you get close, then the problem starts becoming hard. And so what we see here is that the first thing that happens is that our linear systems become harder to solve. Now, so far in pilot, this has not been so much of an issue in fault friction because the systems are so small, we beat them with a hammer. But when we try to run, problems with maybe hundreds or thousands of faults on very big machines, this type of behavior will come up because the linear systems that we get will become more ill-conditioned. So what we can do is we can hit it with the hammer, like we do now in pilot. Let's just use LU. And what we see is that's not a panacea. It allows us to solve the individual linear systems, but the nonlinear equation, even with that gradient information, is not converging. You can see here that you'll just stagnate. So what do? Well, there's a lot of things that people have thought of doing. For instance, this strategy of coarser problems or stuff like that, and that doesn't work. Quasi-Newton is worse, And so that doesn't work. The Picard iteration doesn't work. So we're in kind of a bind here. And this has historically been what happens to people when they're faced with a problem like this. They say, well, I don't have very many good ideas for what to do. A lot of times what people will do in this situation is continuation. They might say, well, maybe I can ramp up the parameter. Maybe I can take the solution from Grashof 1e to the 4 and use it for 1e to the 5. So that would be great, but it turns out it does not work here, and it's because of the way that the problem looks, the bifurcations. The solution to 1e to the 4 doesn't look anything like the solution to 1e to the 5 because, some convection role may choose to go the other way. And so it doesn't work here. It does work in some cases of, say, nonlinear viscous behavior where you sort of ramp up the viscosity, but in others it doesn't. So you can try these, but they're not great options. And so this is where it stood, I say, up until maybe 10 years ago or even later. So if your nonlinear equation is not converging, it may be because your Jacobian is wrong. However, in PyLith, that would never be the case because we don't have bugs in our code. The linear system might not be solved accurately enough, as you saw, so you should try to get an idea how accurate it is. This KSP Monitor True Residual is a really great tool, and you can just put that straight in the PyLith config file. And what that does is it tells you how big the residual is without your preconditioner. Preconditioners can actually distort the information, and they're supposed to a little bit. They're supposed to make the problem easier, but sometimes they can hide an inaccurate solution if they become almost singular. The Jacobian could be singular, so you could have phrased the problem with a singular Jacobian. You can actually do this in PyLith if you don't put enough constraints on something, like a block that can slide straight off. Will have no resistance to motion along that plane, perhaps, and then you can get a singularity from your formulation. Or you can just have a nonlinearity that's really strong, which is what I showed right there. Okay, let's see. It's hard for me to find my mouse sometimes. So in the linear solver world, we saw that we can use preconditioners to help the solver out. And in the nonlinear world, we can now do the same thing. This is new in PETSI this year, and we can help nonlinear solvers by coupling them to other nonlinear solvers through kind of a preconditioning. So let me go past that. Let's just look at the specific problem we have. This problem is just not working. I'm going to back off the Grashof number a little bit. Even 5 times 10 to the 4th doesn't work. Rayleigh of 50,000, it stagnates to. So what we can try is solve this business of solving on coarser grids. And instead of being called multigrid here, it's called the full approximation scheme, which is also called nonlinear multigrid. And we'll use on each as a solver on each sublevel, we'll just use the Gauss-Seidel iteration. And here you can see that it initially starts to converge, but after a while you get divergence of the inner iteration. So what's going on there? Well, what you can do to investigate, so you might get this and you might say, I have no idea what this means. So we have lots of nice ways of investigating. So for nonlinear equations, you can always ask it to print the reason why it converged or did not converge. And you can do the same thing for linear equations with KSP, as you saw in my previous slides. And this is a great way to investigate. So here we say, oh, well, this converged fairly well, but then for these other steps, what happened is it diverged, but we just kept marching along anyway, which worked okay for the time being, but then it just sort of petered out as a strategy. And here it said that the individual Newton solves that we're doing on the course grids did not work because the line search failed. Well, we could say, well, why don't we just turn off the line search? We can do that. And so all of these guys on the course grids converge, but the converged solutions are not all that great. And so the outer iterates are still diverging. So this is sort of all this work, and we're still not working. Is sort of, you get a little defeated. But what we can try is we can say, well, what if we took this strategy and added a very weak preconditioner, but a preconditioner? This is the equivalent of the Jacobi linear preconditioner in some sense. It's the nonlinear Richardson. So if you know what Richardson extrapolation is, it's very much like it's the simplest iterative thing you can do. So we'll just do one simple iterate of nonlinear Richardson on the outside and precondition it with this this nonlinear multigrid. And here we see that we can actually converge. And what happens, you can see, because we have this internal monitoring turned on, you can see that it does get very hard in some of the first few iterates, but this Richardson is able to keep the nonlinear multigrid within the domain of convergence, even if the problems get hard, so that eventually they get easy and we can converge down to the true answer. And in fact, we have a suite of these, so you can change that instead of using this very simple Richardson. You can use nonlinear GMRes, and you can have the number, or take the number of outer iterators to converge down much lower. So this is our idea. And then you can say, well, let's actually use the sledgehammer on the coarser grids, and instead of just doing these Gauss-Seidel sweeps, let's do a full Newton where we just run 20 iterates of it and don't care whether it converges, just keep stepping, and that can bring our total solve outer iterates down to 5. So this is very much like our situation in the linear systems, where you can ramp up the power of the subsolves and add a pretty good combiner like this nonlinear GMRes at the top level, and you can beat these tough systems. And I will tell you something. I know you guys don't think this is as amazing as I do, but I'll tell you what. This is what the situation was when I showed up at Argonne, and no one knew what to do for this system. We just said, we're just not going to solve that. It's not. The mantra was, it was not meaningful to solve these because they're too ill-conditioned, they're too crazy. But we see that, with some pretty elementary technology, we can solve them now. We can solve them fairly efficiently. So I think people are going to change their tune. Now maybe they say, well, yeah, of course they're meaningful. It's just, they're harder. So I'm really excited by stuff like this because it hasn't yet made it out to the applications areas. And so there are a lot of hard nonlinear systems that people really aren't solving because they don't have this kind of technology. And one of the first things I'd love to apply this to is the fault friction solve, because it is very hard, as you'll see when Brad goes over it. So I'm not going to talk about fault friction today, but if it's failing, this is the place to ask your questions, and feel free to ask solver-based questions to this list. There is also a PETSI list, but this list will be specific to pilots, and I think it's the right place to start pilot solver questions. If they become more general, we can move to the PETSI list. So that was the end of my slides. Are there any specific solver questions? Because we have some time.